And our next speaker is Kimura, and he will bring us into the frame of Bell inequalities and the connection to measurement dependence. So please go ahead.
Thank you. Do you hear me?
We can.
Okay, so thank you very much. So first of all, I'd like to thank the organizers for giving me the opportunity to talk. It is always a great honor to speak at this traditional and important symposium. So today, I will talk about a generalization of Bell's theorem, recently initiated by Professor Hall, which shed new light on the Bell's theorem, I think. And the title of my talk is the relaxed Bell's inequality as a trade-off between measurement dependence and hiddenness. Okay. This is based on the joint work, just put it on the archive yesterday with my ex-students, Yugo Suzuki and Kei Morisue. Okay. So this is the outline of today's talk. And first, I start from a quick review of the Bell's theorem and introduce the Hall's idea, which generalized the Bell's inequality, which was called by Hall himself a relaxed Bell's inequality, as a trade-off relations between the quantitatively measured underlying assumptions. And after sharing some problems, I'll tell you the goals of this study. And second, Hall's inequality is introduced in detail, and which generalizes the famous Bell's CHSH inequality. And thirdly, let me introduce the measure of the hiddenness, which reflects the degree how much we need a hidden variable. And we show that we show our new relaxed Bell's inequalities, which gives a non-trivial trade-off relation between the hiddenness and measurement dependence. And if I have a time, I also present a sketch of the proof. Okay, so let's get started. So in 1964, Bell addressed an interesting question of whether a concept of reality is, which is a sort of objective existence independent of an observation, was necessary, like in classical physics, to understand the world of quantum physics, following the famous discussion by Einstein, Podolsky, and Rosen. By considering locality as well, which is of course a very important assumption for us, because we human being is a very local being in the vast universe. He found an interesting inequality, nowadays called the Bell's inequality. And importantly, the inequality consists of experimentally accessible quantities. Thus, the validity of the inequality can be directly verified by experiments. And since the discovery of Bell's theorem, many experiments, notably by Aspe, have confirmed that some of quantum correlations violate the inequality, and consequently, it is widely believed that our world cannot be explained by a local realism. So one important remark is necessary here. There is indeed another indispensable assumption for Bell's argument, that is the free choice assumption, or measurement independence, following the Hall's terminology. Some of you might want to interpret this as the existence of our free will. But anyway, notice that this assumption is often misunderstood as a mere loophole, but it is one of the essential assumptions that cannot be removed in principle in the Bell's argument. Indeed, there can be the case where the statistics of the measurement settings are strongly correlated with the hidden variables, but in experiments, they appear to be random and independent. Therefore, the violation of Bell inequalities imply that the incompatibility of these assumptions. So in other words, to understand our world, we must give up at least one of the assumptions of reality, locality, or free choice. And this result itself is quite surprising, of course, and some people consider this as the most profound discovery in the history of science. However, come to think of it, Bell's theorem with the experimental results tells nothing about the extent to which these underlying assumptions are violated. And in response to this problem, Hall came up with a generalization of Bell's theorem by introducing quantitative measures for each underlying assumption. The assumptions he adopted were determinism, locality, and measurement independence. In fact, sorry, something is strange here. If you go back to the Bell's original paper in 1964, causality and locality are explicitly mentioned assumptions, where causality here means the determinism, and locality means a sort of no signaling property in the level of hidden variable, which is sometimes referred as parameter independence. Let me read aloud the relevant passage from his paper. It is the requirement of the locality, or more precisely, that the result of measurement on one system be unaffected by operations on a distant system. And he also refers here to Einstein's word, which says the real factual situation on the system S2 is independent of what is done with the system S1, which is spatially separated from the former. Okay. But on the other hand, the assumption of a free choice or measurement independence was not mentioned in the original paper and just implicitly assumed. Okay. So Hall introduced 3 measures for these assumptions: I for indeterminism, S for signaling or non-locality, and M for the measurement dependence, and found a generalized Bell's inequality incorporating all these measures. This inequality was called by himself a relaxed Bell's inequality. And in case where all these measures are 0, namely the case assumed by Bell, this inequality recovers the usual Bell inequality. But in general, these relations provide a trade-off between experimentally accessible quantities and underlying assumptions, which allows us to discuss the extent to which each assumption should be violated with the given violation of Bell's inequality. Okay. So I think Hall's result is quite interesting and important. At least it sheds a new light on Bell's theorem. However, we think that there are some problems. Note that nowadays the Bell's theorem is fully formulated not only for deterministic but for stochastic or probabilistic local hidden variable theories. Hence, the determinism seems to not be an essential assumption behind the Bell's argument. Instead, we think the very fact of the introduction of the hidden variable is an essential assumption in itself. So it is necessary to introduce a measure of how much hidden variables are needed. Moreover, for general stochastic LHV, it is known that Bell's locality is not equivalent to the parameter independence or no signaling properties, but we also need another independence called the outcome independence. And here the parameter independence or no signaling means that the local probability is independent of the local measurement context, while the outcome independence means that the local probability distribution is independent from the remote outcome. And it is not so difficult to show that the Bell's non-locality, without p lambda, these two conditions are equivalent. I think that this was first noted by Jarrett or independently by Edward Nelson. So we need a new measure for non-locality, not only for parameter independence. By the way, there is a good reason why Hall only considers the parameter independence. Indeed, in the deterministic model, which Bell assumed, the outcome independence is automatically satisfied. So we can only consider parameter independence. But in any case, since he is also dealing with a non-deterministic case, I think this assumption also must be eventually be taken into account. Okay, so our goal is to introduce a measure of hiddenness and also revise the degree of non-locality and derive a relaxed Bell's inequality incorporating all these measures. Unfortunately, we have not yet succeeded to derive the most general result, but as a partial answer, by restricting ourselves to be a local model, we found an interesting relaxed Bell's inequality that gives a non-trivial trade-off relation between the experimentally accessible quantities and hiddenness and measurement dependence. That I would like to share with you. Okay, so now let me introduce the local hidden variable theory in more detail. Consider a bipartite system for Alice and Bob, where they can choose measurement settings X and Y, and obtains measurement outcomes A and B, respectively. The experimentally accessible quantities here is a joint probability, PAB, with a given each measurement context, XY. By the way, when talking about Bell's theorem, we always assume implicitly that they are sufficiently separated. And usually the measurement events are supposed to be space-like separated in the sense of relativity, in order to avoid the possibility of direct propagation from each other. And hidden variable theory assumes that there exists a hidden parameter lambda, such that the empirical probability is derived by averaging over the hidden variables like this. And in this talk, I use a summation symbol here, as it turns out that the case where the number of hidden variables is finite is interesting. But of course, in general, you should replace it by the symbol integral if necessary. And in the local hidden variable theory, or precisely with measurement independent assumption, we also require that the hidden variables and the measurement context are independent, and also Bell's locality, which simply says that joint measurement are independent if we fix hidden variable lambda. Okay. And as I told you, this is equivalent to the parameter independence and outcome independence. Okay, and the simplest Bell scenario for arguing Bell's theorem is the so-called CH setting, where we have a non-trivial correlation. And the CH setting is a bipartite case where each observer has only two kinds of measurement, labeled by 0, 1, and also measurement outcomes are two valued, labeled by ±1 here. And in this case, the interesting statistics is the so-called CHSH value, where this bracket denotes the average product of each measurement outcomes given measurement context. And trivially, it is upper bounded by 4, but in 1969, Klauser, Holm, Shimoni, Holt, following the Bell's argument, showed that for any measurement-independent local hidden variables models, it is upper bounded by 2, which is the famous Bell-CHS inequality. By the way, this is not only the one of the Bell's inequalities, because usually the Bell's inequality, including the inequality derived originally by Bell himself, is just a necessary condition from these assumptions. But the CHS inequality, actually the set of CHS inequalities, by changing the position of the minus sign, is shown to be equivalent to measurement-independent local hidden variables theory. I think it was Fine who first recognized this. So this makes the Bell-CHS inequality special, not just only one of the Bell's inequality, but deserves to be considered in detail. Okay, so now let me introduce the Holt's inequality. So he first introduced the 3 measures for indeterminism and signaling and measurement dependence. I do not go into the details, but for indeterminism, it is a degree how much local probabilities are close to deterministic. And for signaling, it measures how much local probabilities are dependent on the remote measurement choices. For instance, the signaling from Alice to Bob is measured by the maximum deviation of the local probability of Bob by changing the measurement context by Alice. And measurement dependence is also a measure how much measurement choices are dependent on hidden variables. And with these quantities, Holm derived the following relaxed Bell's inequality in the CHS setting, where the CHS value is upper bounded by some strange quantities, including all these measures. And also he shows that this inequality is tight. And to understand the flavor of this inequality, so first let us consider that all the measures are 0, namely the measurement-independent local hidden variable series. Then the right-hand quantity is in this case, and plugging I and M0, we get 2, and that reproduces the Bell-CHS inequality. But even if you stick to the local hidden variable or deterministic deterministic local models, if you relax the measurement dependence, CHSH value can exceed 2. So that implies that the measurement independence is an essential, one of the essential assumptions that cannot be removed in principle. Okay, so now following the goal I mentioned before, first let me introduce the degree of the hiddenness. And our idea is quite simple. We define the hiddenness by the number of the hidden variables, -1. And we think this reflects the degree how much we need a hidden variable. And for this takes only the discrete number. And for the minimum numbers, where we have only one hidden variable, corresponds to the case where we do not introduce hidden variables. But as a non-trivial case, where h is 1, we have 2 hidden variables. So you can imagine that our world has a kind of 2-sided aspect, like a head or tail, whatever you call. And our empirical statistics is derived by averaging over the hidden 2 variables. And when H is 2, we have 3 hidden variables, and so on and so forth. Okay. And our first result is about the optimal CHSH value for any local models. For any local models, the CHSH value is upper bounded by these quantities, and the equality is attained by some local model. And I skip the proof, which is simple, but this, by local model, I mean that our empirical probability is given by this one, where we only assume the Bell's non-locality. Bell's locality. And because this inequality is tight, we can interpret this right-hand side as the optimal CHSH quantities amongst the local models. And if you remind the definition of the measurement dependence, you see they only include the probability of lambda given measurement context, and this makes the problem quite simple, because we can only focus on this probability. So we have done some numerical simulations by generating these probabilities. And skipping the trivial case where H is 0, if H is 1 or the two-sided world, it seems that measurement dependence and the optimal CHSH has a linear relation like this. But for larger hiddenness, the allowed regions seems to be expanded like this. And for larger H, it seems the regions are larger and larger, but from numerical results, we cannot say anything anymore. And with these numerical results in mind, we have proved the following analytical results. So first, we obtain the lower bound for the optimal CHSH value. For any hiddenness, the optimal CHSH value is lower bounded by the measurement dependence plus 2, and the equality is attained by some local models. And let me skip the proof, but it says that there always exists a local model where CHSH value can reach at m plus 2. Okay. And the following is our main result on the upper bound for the CHSH value. For any local models, CHSH value is upper bounded by these quantities, which includes hiddenness and measurement dependence. And the equality is attained by some local model. Therefore, this inequality is a tight one. And before giving the sketch of the proof, let us first explain what we can say from this result. Firstly, if measurement dependence is 0, namely the case where the model is measurement independent local hidden variable, then just plugging m is 0, right hand side is 2, so we recover the Bell's CHSH inequality. Second, if H is 0, namely without any introduction of the hidden variables, again we have the Bell's CHSH inequality because our model is local. And interestingly, the structure of the dependence of the H disappears when H is greater than 3, or the number of the hidden variables is greater than or equals to 4. And the result is this one, because this is 3. And this coincides with the Hall's inequality by putting IS is 0, namely the models of the local deterministic model. But this does not mean that our result is just a corollary of Hall's inequality. Okay, and in general, our result gives you a non-trivial trade-off between the CHSH value and hiddenness and measurement dependence. to understand this, imagine that you have an experimental result, for instance, where the CHSH value is about 2 square root of 2, which is indeed the maximal quantum violation. Then the point that the measurement dependence and hiddenness can measurement dependence and hidden variables can lie is in this red region. So for greater than or equals to for h greater than or equals to 3, m, the measurement dependence should be greater than this value. But if you want to explain our statistics like this with less hiddenness, then m should be larger and larger. So, and vice versa, if you want to make measurement dependence less and less, then you need more and more hidden variables. So it's quite intuitive, I think. But the disappearance of the structure dependence of h when h is greater than or equals to 3, it's quite interesting and quite non-intuitive, at least for me. Okay. So by using the rest of the time, let me give you the sketch of the proof. So our main results can be rewritten like this. But for the trivial case, it is easy to show that the measurement dependence trivially disappears and the optimal CHS value is 2. So this trivially holds. And for the case h is 1, we can directly show that the relation between optimal CHSS value and measurement dependence. This is elementary, just a direct computation. And for the case where h is 2 and 3, we need some lemmas. And I do not give you the proof of this lemma, but we use some combinatorics trick and as well as the property of the probability. And rewriting this inequality, we get this one. But the right-hand side is the optimal CHS value. And this is upper bounded by these quantities, which completes this program, this inequality. And to prove this, I want to point out that the measurement dependence is essentially given by the total variational distance, where it is the kind of statistical distance between two probabilities, which is defined by the maximum difference of the event probability between P and measured by P and Q. So applying the event, in this case, the singleton, which is composed of this single lambda star, we have this quantity is upper bounded by the total variational distance and have this upper bound. And for the general case where h exceeds 4 or equals to 4, we can reduce the problem to the case h is 3 by introducing the following partition of the measurement, hidden variable set. And skipping the details, we can make this problem to the problem where h is 3, and this is down. Okay, and for the tightness, we concretely construct the models which attains the lower bound and also upper bounds, like this. And moreover, the feasible regions are these red regions surrounded by lower and upper bounds. And technically, this was not so trivial. Actually, we constructed the models which attains any point sandwiched by these regions, combining the tight models for upper bounds and lower bounds. But both the measurement dependence and the optimal CHS values are not affine for the probability of hidden variables. That makes the problem quite non-trivial. So we need to use some trick. But anyway, this is the feasible regions. Okay. So let me summarize. my talk. So we introduced so-called the hiddenness, which reflects the measure how much we need a hidden variable. And we obtain the relaxed Bell's inequality for local theory as a trade-off relations between hiddenness and measurement dependence. For future works, we first want to revise the definition of H for hiddenness. We think this is too simple. For instance, imagine we have hidden values, which has 5 hidden variables set. But if the probability for lambda 3, 4, 5 is negligible, then we need to essentially think that this is the case where H is approximated to 2. So as one idea, we can use the Shannon entropy, and this is the lower bound of our simple hiddenness. And imagine, we can expect that our result still holds for this generalized H prime. We have done so far some numerical experiments, but unfortunately, we found a counterexample for this inequality. So we need to revise this inequality if we want to use this hiddenness. Okay, and of course, our final goal is to derive the most general relaxed Bell's inequality with hiddenness and non-locality and measurement dependence. And for that purpose, we need to revise the definition of non-locality, incorporating not only the parameter dependence and also outcome dependence. Okay, so thank you for your kind attention.
Yeah, thank you very much for this talk. Another one on things we learned during the elementary ways of coming to grips with quantum mechanics. And obviously, these Bell inequalities still have some surprises in putting them into a more generalized frame, just as we heard with the rotating wave approximation in the first talk. So thanks for widening the horizon. And I think there will be questions. So since I might not see all the risen hands, please just go ahead. Yeah, Mr. Hall.
Oops. Hi. Oh, sorry, I'm just trying to get the video going. There we go. Yeah, well, I enjoyed the talk, of course.
Thank you for listening.
The subject dear to my heart. And I like that definition of H prime very much too. That looks very promising, where you can say something about even continuous lambda, perhaps, as well. I did have a question about, or a point to make really, which is that some of these measurement dependent models, although they satisfy locality, as in your examples, they don't satisfy no signaling at the observable level. So it's very interesting that you've shown you don't need more than 4 hidden variables for the Bell inequality. But in fact, if you want to make the model non-signaling at the observable level, it seems that you have to add more. You have to double your number of variables. It's hard to explain in this setting, but I'll send you an email just to explain what I mean there. So in one sense, it may be desirable for you to allow up to 8 variables to avoid that problem.
Yeah, so there was a question by Martin Haringer. He asks whether you think that locality was more important to Einstein than free will. So that's probably something like a philosophical question.
That is quite interesting question. But of course, just so we can imagine what Einstein imagined. But at least I know from this many literatures, Einstein seems to believe the determinism. So in that sense, free will is incompatible with determinism. So I'm not sure, but maybe he does not believe the free will. Maybe Professor Hall, can you comment on this?
Now, I can't second guess Einstein. I mean, he did love, as you say, determinism in the EPR paradox and locality. So I think he might have been perhaps more willing to give up the free choice assumption than others, but it's a strange thing to give up, of course, unless you're an eavesdropper building a quantum encryption device. If you buy one off the shelf from certain governments, it's quite easy to set up those devices to so that they don't operate according to measurement independence, and they do act completely locally and deterministically. So that government can eavesdrop on your code that you set up with QKD. But yeah, Einstein, of course, as Thomas said, is much more philosophical thinker.
Yeah, but I think the point behind these Bell inequalities, say if one might guess what Einstein's perspective was, is that quantum systems macroscopically separated would never ever be somehow entangled or would have had phase correlations. And that's what he thought would be broken by macroscopic distance. And I think that's the essence of all the Bell inequalities, that if you even detect a pair of, say, entangled photons or transitions by radio telescopes on different continents, you still might have EPR correlations until you measure. So I think that's really the point. And he probably will have, just as you said, Professor Hall, or as you said, believe in locality and simply say that macroscopic distance breaks any type of quantum correlations to begin with. And that's, I think, the essence of the Asper experiments, that you do have phase correlation giving entanglement between macroscopically separated quantum objects. So in this regard, I think locality is more essential in the entire picture of Bell inequalities than is free will.
Yeah. Yeah, that sounds reasonable.
Maybe I might raise one little point if there's no further question from the audience, which I don't see at that moment. And that is, in your generalized Bell inequalities, are there any prescriptions to how to set up a measurement in order to saturate your bounds? In a way that we have not been seeing in traditional Bell inequality type of experiments?
Yeah, actually, I think no, because our results always assumes the hidden variables, which is in principle hidden for us. So this does not tell us the kind of genuine states. So in the real experiments, I'm not sure how we can have information how the quantum states have the potential correlations. That's what we need to do the experiments. Of course, we can construct quantum mechanical situations where CHSH value can violate maximally. But what I mean is that from our results, it is difficult to say something about the experiments.
Okay. Yeah, because I think that would be really interesting if you could deduce something on how to devise experiments that really saturate your bounds.
Yeah, of course, nobody knows that in future physics or new physics, we might have some hidden variables which complete quantum mechanics, like Einstein dreamed. But it's just imagination.
Yeah. There was another comment, Michael?
Yeah, just another quick comment, since there's time. You're right to draw a distinction between whether one assumes determinism or whether one assumes outcome dependence, that stochastic condition. However, in some sense, it doesn't matter in the end. If there is a stochastically factorizable model, then there is a deterministic model. So dealing with one case, in a sense, deals with the other case. What I do like about outcome independence, though, you can show in some sense when you try to characterize outcome independence, you can do so independently of the other concepts. Whereas when you try to characterize indeterminism directly, it turns up to be bound up or correlated in a fundamental way with signaling. So yeah, just a point that determinism is good enough in some context.
Mm-hmm.
I see. Okay, thank you very much.
Yeah. Yeah, since we have a little bit of time left, may I turn around the question I put before? The Bohmians usually appreciate these non-local pilot wave type of way of having hidden variables. Is there anything you would be drawing from your picture in as much as how to devise a measurement to explain certain results with these types of pilot waves in the Bohmian sense, which you could not explain by the ordinary way, where you discard of these type of considerations? I think that's a general question that has been open for quite some time, and the current understanding is that there's no experiment you could design in order to really show the need of some type of pilot wave description with non-local hidden variables. So would you be able to give those people a hint of how to devise such an experiment to save the Bohmian theory, and making it even necessary to explain the experiment rather than the conventional picture?
Actually, honestly speaking, I don't have any idea now, but if I correctly remember that Bohmian mechanics is a completely signaling one. So it can instantaneously, the influence can instantaneously propagate to distant place. Am I correct? I don't know the relativistic version, for instance, for the Bohmian mechanics.
Yeah, so, I'm also not totally into that as well, but since you are proposing a generalized theory, I think this would be one of the valuable guidelines if something like this could come out. And on the other hand, of course, also in the contrary, if you can disprove that you can find any kind of experiment that really shows pilot waves at action, which is probably what everybody believes.
Yeah, so maybe my answer now is that not only for Bohmian mechanics, but for any hidden variable models, we can compute signaling or indeterminism or hiddenness and so on. And then we can derive the trade-off, especially for the measurement dependence. So for instance, we can say something about how much we need to give up the measurement independence, for instance. So that's all, because you know that from Bell's theorem, we cannot say, we cannot derive any conclusion for any sort of assumption itself. For instance, we cannot say locality should be hold or not, but combination of some assumptions can have some non-trivial results, which is directly checked by experiments. That's one of the, how can I say, I cannot to exaggerate that combination of assumptions can be verified in experiments. That's one of the remarkable results of Bell's theorem, I think.
Yeah, the
So
Bell theorem
I
simply
cannot
rules
say,
out. The Bell
so
theorem
only we
simply
can say
rules
the
out.
kind of trade-off between assumptions.
The Bell theorem simply rules out local hidden variables. Okay, but in the interest of time, so if there are no further urgent questions, let us thank you once again.